to make sure you are in the right place. This is the auditorium, and this session is titled A Classical Approach to Science. Our presenter is Miss Rebekah Roundey. She is a school teacher at Faith Lutheran School, the school where I serve as well. So it's a privilege for me to introduce her to you. She graduated from Hillsdale College in 2018 with a Bachelor of Science in Physics and also music. At Faith Lutheran, she teaches 4th through 12th grade science and also serves as high school choir director, does a variety of other things too. Please help me welcome Miss Roundey.
Thank you. Is this on? Yes. Okay. Did everyone get a handout? Or did they? Are there people who didn't get a handout? Oh, that's a lot. Thank you. What's the best way to do this? I have a few extras. I don't know if there are more.
You have more being made.
I have extra copies.
Okay.
Yeah. That would be excellent. Thank you. Thank you very much for coming. In this presentation, I will outline a classical approach to science education. First, by demonstrating that science is best understood as a set of arts, and then by taking the principles of liberal arts education and applying them to science. This approach follows the classical emphasis ad quantis, utilizing both historical documents and observations of nature as sources from which to learn. I intend to present not only an abstract ideal of how science education should be understood classically, but also to provide examples of how this approach might be used on a day-to-day basis in the classroom. Actually, before we start, I would like to define my terms. When I say science, I am referring to modern science, biology, chemistry, physics, astronomy, geology, and life. I'm not using science in its classical sense or body of knowledge or scientia, such as when we refer to theology as clean sciences. When I am referring to science in its classical sense or body of knowledge in a specific art, then I'll use the Latin term scientia. As educators, I think we often stumble when trying to incorporate science into our classical paradigm. After all, science wasn't really recognized as a subject until the 19th century. There's no doubt among teachers that it's an important subject to study, especially for its ability to uncover God's order in the created universe. But sometimes the life sciences, physical sciences, earth sciences, and all the rest are lumped with astronomy and the quadrivial, with the idea that since astronomy is a science, surely the rest of the sciences can fit under its umbrella. This is an unsatisfactory solution. So, to begin, I'm going to first show how science can be understood as an art, and what this really means for teaching it. In case you need a review, art can be defined as imitation Georgic reason, or scientia Georgic practice. The liberal arts are the arts which befit a free man and consist traditionally of the trivium, grammar, logic, rhetoric, and the quadrivium, arithmetic, geometry, basic astronomy. Probably review for all of you. Because class educators are very skilled in practicing trivium. You have a great handle on the practice and teaching the practice of grammar, logic, and rhetoric. But what's the practice of the quadrivial art system? That's an open question because I haven't found a satisfactory answer yet. If one can take tools of art rhetoric and use them in approaching geometry, what does it look like to take the tools of geometry and use them in approaching rhetoric? What does the practice of the art of astronomy look like? Because it's more than just staring at the sky. Fortunately, the 21st century classical teachers aren't the first to wonder how science fits into liberal arts education, so we don't have to reinvent the wheel. As science became recognized as a field in the 19th century, mid-19th century, there is also an advocacy for science education. So we take, for example, the 1854 publication of lectures on science education delivered at the Royal Institute of Great Britain which contained lectures on the importance of physics, chemistry, economics, and more in the education of people of all classes. But it's a lecture from 1858 by Michael Faraday that I think is the most useful for our question. It's entitled, "On Wheatstone's Electric Telegraph in Relation to Science, Making an Argument in Favor of the Full Recognition of Science as a Branch of Education." There's an excerpt from this lecture on your handout, and we'll get to that in a moment. For some context on this lecture, Michael Faraday, who lived from 1791 to 1867, is considered one of the greatest experimental scientists, who worked primarily in electromagnetism and chemistry. However, he had very little formal education, having only learned to read, write, and do basic mathematics at a local school. His formal education ended when he was 13 years old, and at the age of 14, he was apprenticed to a bookbinder. He continued his education through his access to a vast array of books, largely self-taught. In the 1840s, the telegraph system designed by Wheatstone and Cooke was implemented in England, and in 1845, this telegraph system came into public attention. Suddenly, electricity and electromagnetism, which previously had been regarded as merely curiosities to the public, began to be seen as having practical use. Faraday takes the Wheatstone telegraph system as a starting point to discuss the merits of science education. He argues that science should be taught not only because good and useful things, such as the telegraph system, might come of it, but because the study of science is beneficial to the students. As you'll see in the excerpt on your handout, there are three main things which science teaches according to Faraday. Let me pull it out. One, to be neglectful of nothing, for small beginnings precede the great. This is demonstrated throughout the history of science, as great discoveries and great developments come either from the noticing of something small or the drawing together of many such small things by others. The second thing that science teaches is to be able to make comparisons between small and great, where the small contains in principle the great as the great does the small. If you're familiar with Faraday's The Chemical History of a Candle, you'll recognize what he's talking about here. If you are not familiar with Faraday's The Chemical History of a Candle, go read it. In that set of 6 lectures, which was intended for a young audience, Faraday uses a small, everyday candle to introduce great scientific concepts from combustion, electrolysis, to even cellular respiration, and the like. The third thing that science teaches is to discover and obey law, applying to the greatest what we know of smallest. This is done through the careful determination of principles and understanding when a principle should be held firmly and when it is inconclusive. This is perhaps my favorite of the three, because applying to the greatest what we know of the smallest is an excellent way to think of inductive reasoning. We can easily take Michael Faraday's description of what science teaches and translate it into classical education jargon. Science teaches a set of arts, not merely facts, figures, grammar, equations, but this whole set of arts, which sound remarkably similar to the quadrivial arts. For example, the art of being neglectful of nothing, which is essential in making good observations, and the art of astronomy, which includes the observation of the cosmos, or the art of comparing small and great, which, when done mathematically, is the art of arithmetic. It would be foolish to try and shoehorn these arts which science teaches, according to Faraday, into a perfect correlation with arithmetic, geometry, music, and astronomy, but we do start to see an intersection, or at least a correspondence. What is done ideally in the science classroom, then, is not merely teaching a body of knowledge, as in the classical scientia, nor is it studying the causes of natural phenomena, as in natural philosophy. Because remember that philosophy is meant to be studied after a mastery of the arts. Rather, it's learning and practicing these arts. The liberal arts are beneficial for everyone, as advocates of classical education have shown, especially through the trivia. Similarly, the arts taught and practiced through science are a benefit for everyone, not only those intending to pursue a scientific vocation. Having recognized the study of science as the practice of the set of arts, we can take what we know of an education in the liberal arts and apply it to science. What we find is that a classical understanding of science education is not very different from any other subject. Literature is a useful analogy here as we trace out the steps and goals of an education in science. To cultivate a future love of reading and build a solid foundation in literature, we start with good and beautiful books and stories which delight and teach. Likewise in science, we start with the wonder and awe of creation and observations which delight and teach. When exposed to this vast variety of distant phenomena, a curiosity is developed, which will make the adventure of vocabulary perhaps not easier, but definitely more relevant. Just as the student's desire to read must be encouraged, this imaginative curiosity must be encouraged. There's more than enough scientific content, even just to be familiar and directly observable, that this curiosity will never run out of subjects to explore. When choosing books for students to read, teachers aren't just content with finding nice stories, but look for books that are well written, with clearly discernible themes, and are overall well crafted. Similarly in science, students should be exposed to, or even saturated with, examples of well-done science. One way this can be done is through introducing concepts in the context of how they were discovered, such as how Rutherford Geiger and Marsden showed by the scattering of alpha particles that the atom must have a nucleus, or how John Snow used contact tracing to determine that cholera was spread by contaminated water, or even how modern astrophysicists use the rotation of galaxies to develop the theory of dark matter. Every scientific fact, law, or theory has a path to how it's uncovered, and that path is usually far more intricate and useful in understanding the methods of science than a short textbook summary might imply. This saturation in well-done science can also be done through imitation, and I'll have examples of that in a moment. A class in which students merely read the great books, but are not expected to write, loses the opportunity for students to practice the arts of grammar and philosophy rhetoric. A class that expects students to merely write without giving them the example of better authors denies them models of experts to guide their own efforts and leaves them without an understanding of the tradition they're inheriting and continuing. Science education, too, should be a constant interplay between absorbing and doing. Students must have the opportunities to practice the arts of science, but they still must be able to memorize vocabulary, use equations, label diagrams, and the like. That is, they still must know the scientia, the body of knowledge used by science. In his lecture, Michael Faraday paraphrases Francis Bacon on this point, that the scientific student ought not to be as the ant who gathers merely, nor as the spider who spins from her own bowels, but rather as the bee who both gathers and produces. A classical education in science begins with wonder at the natural world and its order, provides examples of how that order is best studied, requires a rigorous understanding of what others have already learned through science, and gives students opportunities to practice the arts of science, including being neglectful of nothing, making comparison of small and great, and discovering the law. How then is this implemented in the classroom? Going ad quantas to the sources is usually a good start, but we have two options available in determining what those sources are. The first option is to look at our primary sources as they're usually understood. In science, these could be books influence optics, even features such as Mendel's experiments in plant hybridization. These are important parts of the curriculum. They are part of being saturated in well-done science and should be read in excerpts, if not in whole. But they are better at teaching the practice of science rather than the scientia of science. And they're certainly not textbooks for learning content. The second option would be to take advantage to have a much broader meaning. Instead of being physical documents written about nature, understand the primary sources of science to be nature itself, its principles, its laws, and its mechanisms. Students study at these primary sources can be guided by secondary sources, such as the books listed above, the understanding how these concepts were put together, or even a good textbook. This is going to look different in different subjects and even for different topics within a single subject. So I'll go through some examples of what this might look like in the lab or the classroom. The first way these sources might be used is through a historical approach. Now the example I'm going to use is a daring one, as I haven't actually used this exact source in the classroom yet. But take, for example, William Herschel's discovery of infrared radiation in 1800. In trying to find the ideal color of tinted glass for a telescope solar filter, Herschel noticed that different colors of light had different temperatures. So he set up an experiment in which he sent sunlight through a prism and then meticulously measured the temperature of each band of refracted light. Whether by accident or by continuing the trend of increasing temperature towards the red end of the spectrum, Herschel measured the temperature just beyond the red band of light, even though no light was visible. He found that though no color was there, a distinct increase in temperature was recorded on the thermometer. He published these results in a paper called Experiments on the Refrangibility of the Invisible Rays of the Sun, reporting the discovery of these calorific rays, what we now call infrared radiation. This could be used in many different ways in the classroom. It could be a demonstration, even with little reference to Herschel's paper. It could be done for a thought experiment or an open question of how do you measure light if you can't even see it? Then by reading his paper and then replicating. It could be used to introduce infrared radiation and thus the entire electromagnetic spectrum in a concrete way, or as an example of well-done science. In reading this paper, you'll be struck by the incredible care he takes in designing his experiment, ruling out anything which could contribute to raising the temperature of thermometers besides the light. Most of his experiment is actually spent in calibrating the 3 thermometers he had to ensure that the temperature changes aren't caused by a fault of one of them. You could point at the leap that Herschel takes in seeing what may have been just an accident or putting the 1 thermometer beyond the red to use as control and grasping its significance. That alone is an excellent example of being neglectful of nothing and finding Another way to use nature as our primary source in the classroom or the lab is by having a very lab-based approach to a topic. One that I've had excellent success with in my high school biology class is culturing and studying bacteria. I use a cycle of lessons, labs, questions, and more lessons, always returning to the ongoing culture that the students have maintained. So I start by showing students how to collect bacterial samples, and then I set them loose throughout the school with sterile swabs and agar plugs. They collect samples from places such as plastic skin and shoes, from toilets, from light switches, from the computer lab, even from Pastor Keyser's office. And then we put these samples in the incubator. As the colonies grow, I use class time for direct instruction in the classification and identification of bacteria by shape, the structure and function of bacterial cells, and other introductory material. Inevitably, some of the samples are going to be overrun with mold or have bacteria in areas of plate that hadn't been touched by the swab. That leads to understanding the importance of sterile technique which students practice in creating liquid cultures of select bacterial strains. When identification of bacteria by the colony shape or color, or by bacterial shape alone is unsatisfactory, I introduce students to the process of gram staining. This is a 5-step staining procedure used by microbiologists as one of the first steps in classifying bacteria. Most bacteria can be classified as either gram positive, it turns purple after this process, or gram negative, it turns pink after this process. Once students are familiar with gram staining, then they're ready to learn about bacterial cell wall structure and how the structure of the cell wall affects the outcome of gram staining. From there, lab time and class time diverge as students use their bacterial samples for experiments such as determining the ideal concentration of antibacterial cleaning agents. With their solid lab foundation, students in class can learn about how to work in lab, such as antibiotic resistance, which is more common in gram-negative bacteria. Through this method, students are doing what Faraday calls comparison of small traits. These small culturing bacteria contains in principle the great, the big picture of microbiology, just as the great contains the small. Another way to teach advantas that can be useful in very specific circumstances is by using free exploration for students to learn a specific piece of information, largely student guided. For example, I have a physics lab in which students are given a variety of equipment, and their only instruction is to construct a pendulum with a period of 1 second. If you need a refresher in high school physics or a pendulum, the period is the time it takes to make one complete swing. The scientage we learned here is that the only thing which affects the period is the length of the string. Not the mass, not the angle of release, just the length of the string. Students using this method get to practice careful determination of principles as they sort through factors which might affect the period. Not only that, but because of the mistakes they make in this process, this is a far more memorable way for them to learn the specific scientia than if they had been read or been taught. The fourth way that these sources can be used, or a fourth way, is through using guided labs and demonstrations to directly teach a concept. Take, for example, the law of reflection. So for something like a ray of light in a mirror, the angle of incidence, that's labeled right there, as the ray of light comes in, is going to be equal to the angle of reflection, right there, as the light bounces off. Instead of teaching the law of reflection, and then having a lab to somehow prove that this is correct, reverse the order of what you said. First, have students do a lab in which they look for a relationship between the angle of incidence and the angle of reflection. When one does this lab, bouncing rays of light off the mirror, there will inevitably be minor errors and uncontrolled variables that lead to these two angles not being measured as perfectly equal. If students go into this lab expecting to find the two angles equal, because that's what their textbook and their teacher said, only to measure them as not being equal, you get the dreaded complaint of, the lab isn't giving the right results. By reversing the order of the two steps, having them do the lab first, they form for themselves the conclusion that if everything could be done perfectly, then the two angles would be equal, even if they never directly measure those angles to be equal. It shows them how lab laws are generalizations derived from observed patterns in natural phenomena. In Faraday's words, they are applying to the greatest, reflection in general, what they know of the smallest, reflection of light in the mirror. I have found this to be the trickiest of the four methods. It requires meticulously written labs and almost Socratic questioning between myself and the students during the lab, and well-designed assessment afterward to make sure that the students actually got out of the lab what they were supposed to get out of the lab. These four methods of teaching ad fontes: the historical approach, lab-based approach, free exploration, and guided conceptualization through labs, are by no means the only ways to implement classical anesthetic science education. But I found them a good foundation. Development of new approaches and labs goes very slowly, as I don't like subjecting my students to being guinea pigs too often. As a result, in 5 years of teaching, this is what I've come up with so far. We've outlined the basics of a classical approach to science education. We looked at examples of how this can be used in the classroom lab, but the question might come up of how can this be practical? There's so much content, so much scantia, and now adding historical sources, adding more labs and demonstrations on top of that. How can there possibly be time? I think the answer to the question of time does not primarily lie in narrowing down the amount of content taught, but in cutting out the labs used. And we'll give you a dramatic pause to think about that, because that is backwards to everything I've said so far. But the vast majority of labs would work better as demonstrations, go faster, and have just as good, if not a greater effect as a demonstration than if it was a lab. If the goal of a lab is to attempt to prove that what was taught in class is true, and the bulk of time in the lab is spent in follow these exact instructions, repeat 5 times, to obtain a result that you already knew was going to be true, consider whether one repetition as a demonstration might be a better use of time. These plug-and-chug labs, as I like to call them, that require little thought and definitely no scientific thought, are found most commonly in the physical sciences. But the same applies to lab activities found in all areas of the sciences, which claim to use hands-on learning to reinforce the student's understanding of the concept. If we return to our pendulum example from before, a standard pendulum lab, and one that I'm guilty of using several times in the past, would have students change the mass at the end of the pendulum, measure the period several times, change the length of the pendulum, measure the period several times, change the angle of release, measure the period several times, so on and so forth. A lab like that does little, if anything, to reinforce a student's understanding of that concept. A study in 2015 of over 3,000 undergraduate physics students found no correlation between doing labs in this style and understanding of the material, as measured through test grades. The conclusion of that research was not that labs should be abandoned, but that educators need to reconsider what they're using lab time for. Now, that study was done on college-age physics students, but I see little reason that the results are not also relevant to younger students in all areas of science. If you're interested in that study, I put the reference to it on your handout. There's been several follow-up studies since then reinforcing that. They just kept expanding their sample size, essentially. I should note, there are very important exceptions to that. Dissections and astronomical observations are examples which come to mind of situations in which a student's knowledge is reinforced through a lab. A lab is always going to teach something, and as in any other part of the curriculum, it's important to identify exactly what that lab is teaching. We've gone over examples of how a lab can be used to teach content. We'll look at some examples of how it can be used to teach the practice of the art of science. But labs can be used to teach other things such as safety, following instructions, graphing, unit conversion, observation skills, or even practicing skills to be used in a future lab. When one removes the lab activities that are simply just hands-on activities, there's time in the year for labs that teach worthwhile material. Back to Faraday. Faraday tells us in his lecture that science teaches us first by tutors and books to learn learn that which is already known to others, and then by the lights and methods of science to learn for ourselves and for others. We've gone over the learning by tutors and books and materials known to others, that is, learning the scientia, but how do we teach students to learn by the lights and methods of science, that is, to practice the art of science? Because arts include making and producing and must give opportunities for that. As mentioned before, you wouldn't teach an English class in which students only read and never write their own compositions. One way you can start showing students how to learn by the light and methods of science would be by example. Demonstrate the process of finding out. When possible, answer students' curiosity with, what could we do to find the answer? And if the answer is carry out an experiment, follow through when reasonable and practical. For example, in my 4th and 5th grade science class, I was teaching them about sound and waves and vibrations. I used a balloon-mounted argon as an example of an idiophone. This is simply a piece of electrical conduit that's anywhere from 4 to 10 feet long, resting on 2 balloons. Those are balloons, not bananas. When struck by a hard object, such as the handle of a screwdriver, it makes a beautiful chiming noise. It's very similar in sound to tubular bells. As I was demonstrating this, a student asked what would happen if we took a round balloon that we had used for a different demonstration and dropped it on the bar gong as it was vibrating. I think their question was based off of connecting sound and vibrations, wondering, is the balloon going to start vibrating? Will it bounce off unexpectedly? I very easily could have answered, nothing's going to happen. But it was more beneficial to answer with first, let's drop it on the bar gong when it's not vibrating. Now let's drop it on the bar gong when it is vibrating. Either way, the students learned the answer to the original question. Nothing happened. But by experimenting or demonstrating this experimentally and explaining my thought process, students were able to see the arts of science in practice and hopefully saw the necessity of having a controlled experiment. Another way that students can practice learning by the light methods of science is by an extension of another lab. My chemistry students recently had a lab on the common ion effect. It was pretty much a plug-and-chug lab. But one of the post-lab questions gave several follow-up options that they were supposed to discuss with their lab partner and choose which one sounded most interesting to them. The next lab assignment required them to take that follow-up option, write a procedure for it, give it approved by me, and carry out that procedure. They already had the first lab to base their procedures off of. They were already familiar with the techniques, but they had to figure out where to change the original procedures in order to accomplish their objective. Another way to practice learning by the light methods of science would be through group experiments. Walking a class through an entire experiment, explaining the whole process, having students participate as they're able. I've done this with 4th, 5th, and 6th graders as preparation for their first science fair project in 6th grade. We choose a question, either from student suggestions or my recommendations, and vote. This past year, my 4th and 5th graders were given the options of some experiment that includes bubbles or some experiment that includes paper airplanes. They voted on bubbles. I then walked them through creating a list of possible independent and dependent variables, ruling out any which might be impractical to measure, and then they voted on their preferred combination of variables. In this case, does the temperature of bubble solution affect the lifespan of bubbles? We decided the procedures that everyone would carry out, and the next class period did the experiment. It is hard to see from this picture. I wasn't planning on using the pictures in a demonstration when I took them, but they're using a straw to blow the bubbles into a tray of water. The water catches the bubble without popping it, and then they can time how long the bubble pops on its own. The really beneficial part of a project like this is being able to see how the project and the procedure can be improved. So after 2 days of collecting data, they were having so much fun the first day, they asked for a second day, we I pointed out variations and inconsistencies I was seeing in how students were blowing the bubbles, and how their time to lifespan, even how they were measuring the temperature of the bubble solution. The students commented on unexpected results they had found that they didn't know how to record. What if one bubble joins with another bubble? What if it attaches itself to the side of the tray? Is there going to be a difference between large and small bubbles? This led to a narrowing down of our variables, a refining of our procedures, and another day of collecting data. At the end of this, students were pretty done with dealing with bubbles. I processed the data. I think the older students would have been capable of doing the averages, but we had well over 100 data points, and I didn't want to make an average up by hand. We found out that, or we concluded, that a colder bubble solution might make bubbles last longer. And then we discussed what could be done to further confirm that result. Similar experiments I've done with students in the past include questions like, does the flavoring of cake affect its density? Does the viscosity of glue affect its electrical conductivity? Most of the time, the results are inconclusive. But the purpose of a project like this is to practice the methods of science. And I like to remind students that inconclusive is a valid result. The fourth way students can practice the arts of science, learning about the light and methods of science, may be one that causes fear in some parents and students' hearts: science fair projects. Certainly, what commonly passes for a science fair project in popular understanding does not aid the student in practicing the arts and methods of science. But when sufficiently high standards are given, and support and guidance is given to reach those standards, I believe the science fair project can be a profoundly useful part of the science curriculum. At Faith, all of our 6th, 8th, 10th, and 12th graders do science fair projects, and the process lasts from the beginning of October to the beginning of March. Students choose a question that is original, that is not Googleable. They have to get it approved by me and signed off by a parent. Throughout the process, they meet with me individually several times, such as when doing background research, when designing the experiment, when analyzing their data. At the end of the project, they go through judging with an outside judge, about 15 minutes of being questioned on their project. And at the science fair itself, they have the opportunity to explain their work over the past 5 months to attendees of the fair. Notable projects that students have done in the past include questions like, does the pattern in which you blow on a cup of tea affect how quickly it cools? Does dirt actually improve your grip on a baseball bat? What's the ideal amount of time for soaking potatoes for the crispiest French fries? Does the ability to curl your tongue affect how many licks it takes to get to the center of a Tootsie Pop? Sadly, that one was inconclusive. While our students do their first science fair project in 6th grade, I believe younger students are certainly capable of benefiting from doing a science fair project. A student does not have to be at a certain level as long as adequate guidance is given. If we return to our literary analogy, you wouldn't keep a child from writing a story just because they aren't ready to write a novel. These examples and many more teach students, or help teach students to learn how to like methods of science, to practice the arts of science. Once these arts are mastered, they can then use them in their science classes, in other subjects, or even beyond the classroom. What vocation is not benefited by being able or being skilled at neglecting nothing, comparing small grades, and discerning patterns? I feel like I've missed some major part of this. In summary, a classical understanding of science education recognizes science as a set of arts and teaches those arts along with their related scientia. To teach ad fontes, we use nature and its laws sources and refers those sources constantly to labs and demonstrations. Students are given the opportunity to practice the arts of science, since once these arts are mastered, they can be used even beyond the realm of science. Of course, this is not necessarily comprehensive, and I hope that this presentation is just part of a conversation on classical science education. So if you end up having questions later, after you think and inwardly digest this, or if you want to share how you have been approaching this, I invite you to email me. My email address is also on the handout. I would love to hear from you, or you can just hunt me down during this conference. I'd love to talk about classical science education. But we do have time for questions now, I think. So what questions do you have? Yes?
Their stuff. How do you manage, so you have the kids all take their own questions. How do you manage guiding each of them in a relatively large class as far as what they do to experience this idea?
That's what a lot of the individual meetings are for. So even from the first meeting they have with me is when they go over their project, or their project selection. They have to come in with at least 3 ideas. And I give them a format of how those questions are. If they're in 6th grade, all the questions are going to be the format of, does X affect Y? Choose an individual and then from that meeting, we're already talking about, do you have plans of how you want to be carried out? When they're designing their experiment, they're figuring that out more. As they do their background research, they're hopefully starting to get ideas. And there's a lot of, I scribble notes down on something for an answer date. It'll all help. Other questions? Yes?
You made a comment earlier about mistakes. How do you approach mistakes? It seems like you don't want to discourage mistakes because, you know, how do you deal when they find a mistake? How do you talk to them and then approach them?
You mean like in a lab?
In a lab or as a process and they can working it through.
In something like the pendulum lab, I very much back off and figure out what works and what doesn't. I only step in if they're really going down the wrong trail. And other things, you know, might point out the mistake and always work towards how do we work through this mistake. I tend to have very bad luck doing labs that are unexpected. So sometimes those mistakes are on my part, and they become a really great learning opportunity for everyone. Oh, everyone's lab just didn't turn out. I'll go home and do more homework on why our titration's not quite on the different results. And then we all end up learning a lot more. So that's another thing of modeling how to work through mistakes. Yes?
Can you give a concrete number, like, you're mostly teaching high school and middle school, right? But what about the younger grades? Does the, like the labs that you'll do with them per year, how many?
My ideal would always be 1 per week. But like high school labs, we are doing 1 per week. Younger grades, 6 and 7, I try to have 1 per chapter at least, of our curriculum, so we usually end up doing 1 every 2 weeks. Sometimes 1 every 3 weeks, but there'll be a lot more demonstrations in there as well.
So you're conflating lab with demonstration, or not conflating, but that's what you're talking about?
What do you mean?
So if you have 1 per week, that means you have a demonstration per week.
No, that would be they are in the lab room themselves doing a lab per week. A demonstration might come up at any time.
Thank you.
Yes.
If you were going to track, may or may not be what you do at your school right now, with how you would develop a child's science education, kind of from the 4th grade level where you start with them through high school. I mean, what would you do as a very broad overview of what topics you're hoping to teach them kind of through those stages?
So like in terms of what content?
Right. So I mean, high school, do you do like biology and then chemistry and then physics? But what are you doing maybe before that to get them ready for those high school subjects?
what we do right now, 6th grade is general science, 4th and 5th grade is general science, 7th grade is life science, and 8th grade is physical science. I really want them to have a foundation in knowing a lot of basic information and understanding these arts. How do we make observations? How do we start thinking scientifically? So in the younger grades, I am trying to go over just a lot of information, and then we'll go deeper in high school. A lot of 4th and 5th grade science, that's when I'm working on designing kind of from the ground up right now, and there are definitely times, what do I feel like teaching about next quarter? I'll choose a topic and we'll delve into it. Yes?
What's your contact time with the students kind of in a given week? Are you seeing them, a couple days during the week? Is it, half an hour, 45 minutes kind of?
Once a day, 37-minute periods. 4th and 5th grade is every other day.
You talked about it a little bit earlier, but what kinds of things do you look for in what should you look for in a science curriculum that's going to be like your foundation? Like, obviously, like, in the way, I don't know. How would you
In a
do it?
curriculum or in a textbook?
Either.
No textbook is going to be perfect,
Right.
but choosing one that I have to argue with the least. For curriculum, I just assume that whatever textbook we have is going to be supplemented. I'm going to be writing my own supplements, we're going to be expanding on it, and that's going to change different topics. So that's probably more vague than if you want to advance the road. Does that help?
I think so.
The follow-up is regarding textbooks and materials. So do you use an eclectic approach? You have your supplements from Fontes, and you have a textbook that you use for your classes, or have you just thrown those away altogether?
There are some textbooks that we have that I'm content with, and they're very easy to supplement. And there's some that I'm supplementing so much that the textbook is a formality. I should sit up the headmaster here. So we still use one consistent publisher. It's different for each subject.
So what's your criteria for critiquing the textbook? I mean,
Does it contain the content necessary, and is it approaching that content in a useful narrative? Some textbooks secular textbooks are generally going to have a much more materialist approach. Some Christian textbooks go the extreme opposite and they choose teaching Christianity over teaching content. So that's one standard. I want to find something that is compatible with doing all these labs. I like the textbook to be just a reference point of all the information students are going to need to know. Does that make sense?
Do you find it useful ever to have your students like read from a textbook, or do you just use those like for your own?
Yes, they do textbook reading, and I think that depends on the class. Especially when it's a topic that either going to be really confusing, I want them to read the textbook thoroughly, so that the next day, you know, now they know what questions to ask. Or if there's a topic that's just going to require a lot of memorizing information, I want them to be supplementing whatever I'm saying in class with the textbook. If I'm just saying what the textbook say, then one of us is unnecessary. But I want to be supplementing the textbook as personally. So I want them to be reading the textbook so they know what I'm adding. Again, it differs for each class.
What do you tend to do for assessing learning? Do you stick with tests? Are you doing a mix of formative and summative? How do you tend to assess what they
So
learn?
far, just straight tests. I haven't read a lot of that.
Are there any courses or levels where you use only original science texts and not?
In our senior level astronomy class, We do not have a textbook. We couldn't find one that was compatible with what we wanted to teach. I do still use things like PowerPoints. I'm working on incorporating a lot more historical documents and a lot more observations that we learned from, but that is a class that we just take just because we don't have a textbook.
Do you move into the philosophy of the scientia and the arts intentionally, or just as it comes up?
I think more as it comes up. There have been times when students ask in lab, and they'll preface this question like, I'm not trying to be disrespectful, but why are we doing this lab? And that gives a great opportunity. Well, this is what we're learning from this lab. This is a tool you're going to need, and it's kind of building off this content you've already learned. So I try to do it more naturally, rather than just at the beginning of the year, this is how I teach science.
How often do those philosophical or theological conversations come up in your classes?
Regularly. I don't know, like, how many times per week.
Sure, that's
It's something that I like talking about, the students know that. Maybe they're just trying to throw me off track, I don't know. But we do regularly have these.
You mentioned the importance of building a sense of wonder, right? Are there any practices or habits that you found particularly helpful in cultivating a feeling of wonder in the kids or helping inspire that?
These are things, science is something that I naturally get very excited about. So I find it very easy to point out things that are exciting and get that into students. I regularly get emails from parents of, my child found a dead spider, do you want it? And I hope that's just that wonder rubbing off. They're looking at their surroundings and asking questions that are interesting. Yeah, it's because it's something that comes easily to me. I haven't really thought carefully about how I approach that.
Can you talk briefly about your laboratory room? What are 5, 10 things that if you don't have one, starting in school, what makes a lab room useful for high school?
At Faith, we're very fortunate to have a well-equipped lab. I'm not sure. And that's something that you don't find a lot of resources for, is what's the bare minimum you need. There's 2 excellent books written. One is the Illustrated Guide to Home Chemistry Experiments by Robert Bruce Thompson, and the Illustrated Guide to Home Biology Experiments. And both of those, they have errors in them, and we regularly find problems with procedures. But a really great strength of it is he'll give a lab and say, here's where you can acquire these chemicals if you can't afford lab grade. Here's glassware you can substitute. Here's how to set up a budget lab. Writing for people who just are amateurs in their sketchy way to do chemistry. But because that's his audience, I found that to be really useful in figuring out substitutions of what do I need for the lab.
So how do you teach evolution? How do you address that? Do you have other classes at the school that deal with that? But specifically in science, how do you approach the errors that are philosophical, foundational errors to evolutionary thinking? And then also, do you engage any texts, original texts that actually support or advocate?
In biology, we read several chapters out of Origin of Species. I think that's really useful. Any conversation that is always going to start with, read a bunch of issues, where our foundation is. We anchor ourselves in scripture, and then it's like a thread of yarn through the class. We wander a bit more and always find our way back. And I think one way, and I'm trying to incorporate this more, there's a lot of ways to approach reference to the foundational errors, but I think it's important to point out where those theories are coming from and how we're looking at the same set of data and we're interpreting it. Some of that is from pre-zones that we have. So I'm trying to incorporate more in this advanced approach, also looking at historical theories that were wrong. That it's really easy to look back and say, well, what were they talking about? It must be so stupid to believe that theory. But when you look at the information they had, you understand why they had these incorrect theories. And I think that helps to have a more comprehensive approach to questions like evolution. Understanding, well, we don't have a scientific approach. We're saying that at some point our scientific method breaks down and can't tell us about what actually happened at the creation. And also understanding where are they getting their theories and how can data support their theory. And that we just kind of throw out some aspects of what we believe. A lot of aspects. Does that answer your question?
It's not a question, just an appreciation for what you're doing here. For these 15 years, I've been in the secular world doing data analysis, fixing problems, something's broken. And you have to do the scientific, you remove a variable, well, work out. And I think the process you're doing is what is the best part, not necessarily the end result, but are they going to be able to see something that's broken, figure out what might be done to fix it? So I appreciate it.
I think we are. Thank you very much.